Okay, so today we will do two things, mainly two things. One is we'll go over two ideas. What? Oh, we'll go over two ideas of time-dependent quantum mechanics problems. One is sudden approximation, another is adiabatic approximation, and then we will we'll do some sketchy examples. And actually, this topic can be very deep, both sudden and adiabatic, especially the adiabatic, because it links to something called Berry phase and Berry curvature, and that is, I think, can take up a whole class. So I'll not go over in details of that, but I'll give a physical idea of what is that, and the rest, the actual details is there in my lecture notes and all these recorded lectures. So we'll just give the idea of these two class of time-dependent quantum mechanics problem, and give some idea of how to solve problems and how they are in practical context. And then, if there is some time, I will initiate the scattering chapter, basically the problem of scattering, and then from next class onwards, I think it will be another 2 to 3, actually 3 lectures for scattering, and I hope I'll get 2 to 2.5 lectures for relativistic quantum mechanics. And as I told you, I will drop the last content of last 3 lectures because I'm taking 3 extra lectures, and that will be basically relativistic quantum mechanics. For exam, I'll drop that content. Okay. So I hope everything is clear so far in time-dependent quantum mechanics. Okay, there is nothing complicated here. It's just a bunch of techniques to solve the problems. The basic idea is all the same. So just spend some time with it, then all these things will be clear. Okay, so now another thing I should tell you. So now we are more or less not going to use perturbation theory ideas, because these problems are not really perturbative. So we will do these two things. First, sudden. These are not actually perturbative problem, because as you can imagine that, as I said, what happens in sudden? Let's say I have this particle in a box. I suddenly doubled the box. So this was L, this is now 2L. This is not a perturbative problem at all, right? So we need some different ways to think about this. Okay, so now let us just tell you that let me state the problem. So I want to go from some Hi to Hf over some time tau. Now I call this time sudden, like if this thing is sudden. Sudden means something happened very quickly or suddenly. So when the tau is much smaller than all other relevant time scales. And in this case, you can think that is basically tau is much smaller than h bar by delta E. Okay? But delta E is the energy gap between two levels, average energy gap, or if you are interested in particular energy sector, it's the energy gap between two particular levels. For example, I'm taking, let's say, particle in a box problem, and I'm interested in this energy scale. So the time scale corresponding to these two energy levels is basically h bar by delta E, where delta E is the gap between these two levels, and tau is much smaller than that. Right? So that when that happens, when the time over which you made the change is much smaller than this time scale, then you call it sudden. Okay? And I mentioned one example in my notes, so let me just go over it. But you see the idea that I mentioned before, that initially if the system is in ground state of this, then I suddenly changed it, and it still remained in that ground state, right? Because it didn't get time to respond, the state of the system. And then I ask what will be the time evolution. So now I have now the state of the system. So this whole thing happened at t equal to 0 instantly. Right? This whole thing happened at t equal to 0. Now the state of the system is not an eigenstate of this new problem. Right? That is the usual case for any quantum mechanical, any time-dependent quantum mechanics. So now I want to ask, after some time t, given this psi 0, which is not an eigenstate of this problem, what is the time, what is the solution. And there is nothing new in it. You know how to solve it. If I give you an arbitrary size 0, you know how to solve that problem. So that's the only change here. So typically you want to know what is the expectation value after some time t. So what you have to do, you have to calculate that expectation value. Typically what you are interested about, some operator at time t. So you have to calculate the psi t. How will you calculate the psi t? You take this wave function as your psi 0, and then you let it evolve under this new Hamiltonian. Then you get the psi t, and that is what will give you. Then you can calculate the expectation value. Right? Everybody got this point? Okay. So this is operationally all the problems. Operationally all the problems. That is what you have to do. Now I will give you a 2-minute idea. A brief detour on where this is useful, but I mean useful in many contexts, but I'll tell you something that I am currently thinking about, so that's what is just more relevant to me. But then let me first give a textbook example. So textbook example is decay of this hydrogen to helium. This is a famous process in star mechanism and all that, like how stars generate fuel and all, like converting hydrogen to helium in this decay process. It emits one electron and one neutrino. And this is He plus because it has one electron in its outer shell. It's one ionized helium. So the way to estimate this is this electron is known to be emitted with this 5.6 keV energy. Okay. So K electron, K eV energy. Okay, I'm very bad with units because I always solve with H bar equal to 1, C equal to 1, G equal to 1, all that. But at the end, one have to match dimension and fix all those things. Okay, so mass of electron is E equal to mc squared. So you can calculate basically using this E equal to half mv square, and you know the mass of electron, so you can estimate the velocity to be order of 0.15 c. If you put all these numbers, c is light velocity, and if you calculate the tau corresponding to that, that is a0 by v. So that is the a0 is Bohr radius. So it is basically the time it takes to escape the dimension of electron. So this is a semi-classical calculation, and that time is, yes. Sorry, what potential energy? No, this is the electron that is released out of it. Okay? So I'm getting a semi-classical estimate of the time scale of the problem, that how long it took for the electron to get out of this. Okay? And now if you calculate the, so now this is the tau, this is the time scale with which the emission happened, right? So now if you calculate the internal time scale, which is h bar equal to delta E, you use the two lowest eigenvalues, you will get that number is of the order 10 to the power minus 17. So basically this is much faster. This tau is much lower than this, and this is a much faster process. So this is a rough estimate that it is 100 times faster, so you can categorize it as a certain approximation problem. Okay, and so then what you can do, so that means after the emission, the electron is still in the state of the helium's ground state. Okay? So if you want to ask the question, so what is the probability that electron is in the helium's ground state? That is given by d3x, sorry, d3x psi naught star. You just take x z equal to 1, the before 1 and the after 1, and calculate its mod square. Yeah. Yeah. No, one is minus 19, another is minus 17. Right? 100 times smaller. Right? Okay. So if you estimate this, you will get 0.7. So there is like the 70% probability that the electron remains in the ground state of the new Hamiltonian. So electron remains in the ground state of helium. So you begin with the ground state of hydrogen. but we are estimating the probability. What is the probability to find it in the ground state of the helium? And that is 70%. Okay. Okay, so this is just one estimate, that if you, one example of using certain approximation. Another example I have discussed here is more simple. This is I have half p square by 2m plus half m omega naught square x square, some oscillator like this, and I changed it to something like this. So this is my initial, and my final is something p square by 2m plus half m omega square x square. Or you can make it more steep, like whatever, some omega which is different from the initial omega naught. Right? Very simple change, but there will be something non-trivial, because now what does it mean? That the ground state of this guy, of the initial one, will become the initial state of the changed one, but that is not necessary, that is not the ground state of the changed Hamiltonian. Right? At time equal to 0, suddenly this change happened. So you can, I will not do the full calculation, but I'll just discuss the solution. Okay, so what are you supposed to do? So you are supposed to use, so notice that what happens. So let's say I have a H, this is the ground state. This is the original ground state, initial ground state, E naught, and this is the final ground. So then it changed to something else, and you want to calculate the effect of, for example, I have a operator A, and the A is the annihilation operator of this problem, the final. Right? So if I have that, then I can convert this into the new problem. And when I do that transformation, so let's say everything about the initial problem, I call them with naught. And everything without naught is basically the final problem. So I can convert this into that of final problem. It will become omega by omega naught. So what is A naught? A naught is something that acts on this ground state and gives you 0. Okay? And A is something that acts on the ground state of this new problem, it gives you 0. So if you can convert them from one to another, this is the conversion, and you can compute anything you want, basically x naught square, using this conversion. Let's say I want to calculate x square, I want to calculate p square. Huh? It's not pi, it's 0 with a cut, but yeah, you can say it's the ground state of the problem before quench. Quench means before the sudden. Yeah. Okay. Everybody got this? Okay. I am under the assumption that these problems are at your fingertip. It should be by now. Okay. If you are finding it strange somewhere, it means you have not practiced the problems. All these things are very simple. So you have to calculate this. Okay. If you will get some number, some function. Similarly, you can also calculate this. So this will tell you what is the state of the system. If it is initial state is this, if 0, and starting with this. So now let's say you are interested. What is this expectation value after time t? Now notice when you are writing this, it's a Heisenberg picture, which means you have placed all the time dependence here. You don't need any time dependence here. So this is equivalent to this quantity, right? Because you have placed the time dependence inside the A. Now, how do you calculate x squared t? Use Heisenberg equation. Right? ddt of these is basically h commute x squared. Right? So do those calculations. These are very simple. I will not tell you all the details, and it's worked out. The answers are given in my notes. But I will discuss one solution, one result which is very interesting. So These problems are very interesting non-equilibrium problems. I'll tell you in a moment why they are interesting. So this quantity xt1 xt2, if you calculate this quantity, this kind of things are called correlation function. So you have learned about correlation functions in some context somewhere, statistics, if not physics. Optics, okay, very good. Yeah, optics is a very good place to study. Okay, can somebody tell me what is correlation function? What does it? It has a colloquial meaning, which means the name correlation function already tells you what is it. There is nothing complicated. Can somebody tell me what is it physically? Hmm. Hmm. Yeah, you are thinking very complicated way. Correlation means correlation, right? Literally that. So 2 points in space and time, how correlated they are. That's it, nothing else. In statistics, you might have learned this in many contexts that two variable. You didn't learn this Pearson rank correlation. What I thought syllabuses are much more advanced at your age compared to my age. Okay, nowhere you have seen correlation function except these optics. Okay, fine. So let's say I have done something somewhere, right? So let's say I have a field, any field in free space, some field. Okay, I have created some disturbance here. Things are propagating and changing. So correlation function is simply the idea. Let's say I take a point here and another point there. How these 2 points are related. So what do? You multiply this function field at point x1 t1 and multiply it with x2 t2, right? They could be completely now if you average it over a time, over some time, let's say. So average it over some time. So then if it becomes zero, that means they are uncorrelated, right? Then they are fluctuating in a way that they are zero. And similarly, it can be very high number or low number. For example, let me give you an example which is right now floating in my mind is let's say a paramagnet, a ferromagnet and a paramagnet. A ferromagnet is a highly correlated object, right? Things are far from each other, but yet they are correlated, right? And a paramagnet is what? Right? So if you calculate a correlation function between 2 points and average it, you will get nothing because there is no relation. When you average it, it will give you zero. Right? But paramagnet that will not happen. So correlation function is simply the idea how 2 points far apart are related. It's a very important quantity. It tells you how much ordered a field is or how much relation is there, interrelation is there between 2 points. Got the idea? Okay. So in general, if you have a very complicated system, then they are tend to be more uncorrelated, right? There are random sources of disturbance here and there. Like for example, if you want to understand atmosphere. Atmosphere is a very complicated system, right? There are various sources of heat, various sources of energy, sink, and all that, right? So it's more likely that the fields will be uncorrelated far apart. But although that doesn't happen in practice, there are very strange correlations appear that are very interesting properties of emergent phenomena, like some sea wave in Latin America affects the summer here, right? El Nino and all you must have learned somewhere. So there are unusual correlation appearing in strange, in complex systems. But the idea is just this: how two fields are correlated. In statistics, generally it is taught in this rank correlation and all that. So, for example, you want to find the relation between two quantities, rainfall and production of crop, right? They are very correlated quantities. So there is a way to systematically study this correlation. It's called this Pearson rank correlation and so on. So anyway, so the point is here, I want to study this correlation function of this position operator at 2 points, at two different points in time. So correlation is one of the most important quantities in any statistical or quantum physics. You will learn that eventually. For example, you will learn linear response theory in next semester in StatMech, and probably you will also learn some about correlation in your solid state physics course, right? You are learning about structure factors, X-ray diffraction, neutron diffraction. So those are basically correlation functions, right? They are basically Fourier transform of certain correlation, 2-point correlation functions. Okay. So you will see that why do they appear there and why they are important. You will see that if I have a system, okay, which I tickle with a small field, let's say some field, small field AT. Okay. Small means I put a delta in front of this, and I want to measure the response of the system BT, and I want the BT as a function of this delta A. Okay. This is expected, right? I tickled a system with an external field. You can think it like, let's say I have a system on which I put on electric field, a charged system with an electric field or magnetic field. I disturb it a little bit, and then the system responds in terms of some current. Right? So then this disturbance will be electric field or magnetic field, and this response is some current. Right? So this is basically what you do in any experiment, right? Current as a function of electric field. And if it is a ohmic conductor, for example, you have learned that J is proportional to E, J is sigma E actually. So this sigma is basically some conductivity, and you can show that this sigma is actually a 2-point, this kind of a correlation function of this, of the internal quantity. So this thing is called linear response theory, and when it is linear response, then J is proportional to E, not some higher power of E. And when this is, then you can use perturbation theory in those problems. When that doesn't happen, then it becomes non-perturbative, and you cannot work with 2-point correlation function. You have to work with more point correlation function, 4-point correlator or something more complicated. So this idea is actually at the heart of anything. Like anything you learn, any experiment, is basically some sort of correlation, measurement of some sort of correlation. The correlation between response and disturbance and that sort of thing. So it's a very important idea. So go over it in your optics again, and it's the same idea. This is another thing you should learn, and you should be aware of this when you are taking physics courses. There are very few things which reappears again and again. In optics, in acoustics, in particle physics, in condensed matter physics, in cosmology, everywhere. Same idea, same correlation function appears in various different forms. Okay? So make sure you go back to your optics course and get a physical picture of what is correlation function. So you must have learned about this Nyquist theorem and this, what is this thing called? There are two functions which are convolution, these ideas, right? You learn those in Fourier transform and all that. So think about this. What are those physically? So you can think this Fourier transform is actually a very physical problem, right? So for example, if I heat this glass, this tumbler, this is a metal, right? So its response is not in real space. Its response is in Fourier space. Why? Because if I heat it, it will produce sound, right? And that sound is a collective excitation of the atoms in it, right? So it's a Fourier space phenomena. It's a momentum space phenomena for this, right? So all experiments. So what do? I want to know what it is made of. Is it made of metal or made of plastic, let's say? So it will have a different sound response, different response to a mechanical disturbance. If I heat it, the heating it is a perturbation, right? A small perturbation. This small perturbation will generate some response. The response is sound, some collective excitation. Right? So the simplest experiment, and it has a characteristic response that tells me that whether it is plastic or metal. Right? So these simplest kind of experiments are basically a linear response in Fourier space. Right? So all experiments you do, starting from here to what you do in LIC, all experiments you do are basically that. There is no difference. So it's make sure that you, whenever you read this in optics or wherever, solid state, any course, anywhere, so spend some thinking about it. What is it? That why you are suddenly taught some correlation function, some convolution and all that. What does it come from? What does it mean? What is physically, you picturize it, right? So this is very important, and make sure to do that whenever you see that. So here I am measuring this correlation function, calculating this correlation function for this particular problem. Okay? It's not just an arbitrary thing, it has importance in it. So if I do that, I will get the following quantity. E to the power I omega T2 minus T1. You might, I don't know if you thought about all these points deeply. You must have spent a lot of time learning about reciprocal space, right? So did you care that why did you spend so much time working so hard about it? You understand that, right? Okay, very good. So then this is basically this idea again. When you excite a system, you get the response in reciprocal space. It could be frequency domain, it could be in space, the reciprocal space is whatever, the lattice reciprocal space and all that. So the picture you get in your X-ray diffraction is basically a picture of reciprocal space. Okay, so if you calculate this, you will get this strange quantity. Now the first term is something you have seen before. It is anyways there. Even if you calculate this quantity for a simple harmonic oscillator, you will get that because it is nothing but the time it takes to go from this point to this point. Right? I omega T2 minus T1. But these two terms are strange. They are basically non-equilibrium term, and one of them even breaks time translation symmetry, which is even more strange because this term is simple. This just tells you it only matters that what is the difference between these 2 points. So if I take a time axis, I don't expect if this is like 11 a.m. and this is 12 p.m. or this is some other time with same time interval, right? So T2 minus T1 basically tells you only the difference matters. But T2 plus T1 is very strange, right? It is telling you when you measure that matters. So it is not a time translation symmetric problem anymore. So why is it there, right? So this thing captures the memory of quench. So this is called some kind of memory effect. So quench means changing something suddenly from one thing to another. Right? So this thing captures the memory of the effect, and this appears because of this kind of non-equilibrium quench. So this point is very interesting. So think about it more. And there are very interesting example of that in other contexts. So there is something called time crystal. So time crystal. So space crystal, you know, right? Space crystal is basically a crystal which is periodically ordered in space. Right? But time crystal is basically, it appears only in non-equilibrium systems. There it can be proven. So you do something to the Hamiltonian, basically some kind of time dependent thing. Then the response of the system has a time periodicity which is not the original time periodicity of the problem, right? For example, in this problem, there is a periodic scale which is omega naught. This problem also is the periodic scale is omega. Now, if it turns out that the response of the system follows a time dependent periodicity, and this scale has nothing to do with omega or omega naught, so then it's kind of an emergent periodic scale, right? Emergent periodicity. So this thing is called time crystal, and they are very interesting. They are very deeply studied in recent time. One of your seniors did a term paper on that. I don't know if any one of you doing that, but it's encouraged to look at into this. Now, all this interesting phenomena appears in this kind of problems, like when you somehow break the equilibrium, suddenly quench it, and the system suddenly absorbs energy from the system or from external or something. Okay. Okay. So there is one more very quick thing. Yeah. So this term captures the fact that a quench was done. Right. That is all I'm saying. And when that quench was done, like what is the time interval? Basically, the measurement of time starts to matter, right? When you measure things, at what time, that starts to matter. Right? So that's why it's some sort of a memory effect in that sense. No, it's an external process. So it is, in this case, it's a spontaneous process, but it is happening because of something else, because you are describing a system using all this hydrogen atom and all, but this process is a decay process that involves weak interaction and all that. Right? So it has some energy exchange between outside and inside, right? Some energy release or energy acceptance, right? So, but in this problem, for example, here I'm doing something intentionally. Like I have an experimental setup, I have an atom in some harmonic oscillator, and suddenly I change the frequency of that trap, or suddenly I turned on a potential or doubled some potential. Right? So this is some kind of thing which I have engineered externally. So both kind of scenarios are possible, that you either engineer or it happens spontaneously. But the main point is it happens so quickly that the system doesn't respond, doesn't get time to respond. Right? So this is basically the idea. This is actually at the heart of all this quantum engineering and quantum technology. You various ways you change the system and how the system responds. And one quick example I'll give you, which is something uh, related to again a technological problem. Technological in the sense it's not like a engineering problem, but it's a place where you can possibly exploit quantum mechanics to do something useful. So the idea is this. Let's say I have a system which is at time hi at time t equal to 0. And I suddenly quench it to some hf at time t equal to 0, both t equal to 0. Right? Then I evolve the system for some time up to hf, at hf up to some time t. So this is my time axis. And then suddenly quench it back to hf. Right? And I ask the question, how much energy is absorbed or released in the process? Right? So initially, let's say I was an eigenstate of hi. I naught. Right? So what happens here? So what do you want to calculate? So the system reaches at some state which is not an eigenstate of hi, right? Because of this process. You got that idea, right? I suddenly made hi to hf. Hi to hf means here it is still I naught. Right? Then it evolves under hf. Okay. And then I suddenly quenched it back here. So then I calculate. So this is basically my energy absorbed. Let's say I call it just E, delta E. This is a scalar. So it turns out the system can take energy or release energy depending on the property of hi and hf. And something more interesting happened if there is a quantum critical point between this hi and hf. So quantum critical point, you probably again is an unfamiliar concept to you, but you know about critical points, right? You know about phase transition and critical point. And they are all temperature dependent phenomena, right? They are all like, I cool a magnet, I have a paramagnet. No, I have a ferromagnet. Yeah, so let me start with the paramagnet. I have a paramagnet. I cool it at temperature, it orders. Right? So, any of you attended this Memba effect talk recently? Nobody. Okay, what's the point of this talk? Huh? There was this colloquium. None of you attend colloquiums, right? Yeah. Okay. What about the next one? Okay. Anyways, so if I cool it, it will reach at this. Right? It will become ferromagnet. Now, this is a classical phenomena because it happens because of temperature. Right? But if it is a quantum phenomena, it could be a quantum phenomena. There are systems where there is no temperature. Temperature is zero actually. It's zero temperature problem. So then I have a parameter which takes it from here to here. So let me give a simple example. A simple example is transverse Ising model. So transverse Ising model is this: sigma ix I plus 1x plus h sigma iz like that. So basically I have a Ising model plus a magnetic field term. So then what happens? This is, let me make it z and make it x. So when h is large, the system want to all orient in x direction. This is large, it all wants to orient in z direction. So there is a point where this transition happens. So this is an example of a quantum phase transition. So if I take my h to be 1, I can say g is the only parameter. So then it can goes from this to this. This is a similar phenomena, but it is not happening because of temperature. So they are called quantum phase transition. They have interesting consequence of that. So now if I between Hi and Hf, if the Gc is somewhere in between, so the system goes through a phase transition here. So then there are some interesting signature in this delta E, which helps me to detect this phase transition. And then there are, this is one problem which is very interesting, that how one can detect that actually a phase transition happened in between or not by calculating this delta E. So what do you have to do? You have to have a setup where you suddenly change the Hamiltonian, which Hamiltonian changing means what? Some potential you have to change. Right? And then leave it under that Hamiltonian for some time. Then you again quench it back and see how much energy the system took or gave. Right? So if you measure this, that quantity will tell you what happened in between Hi and Hf. So these are very interesting problems. There are some other more problems you can think of. You can think of heat engine problems, right? What happened in heat engine? It's basically changing the state of the system, letting it evolve, and again coming it back and all. And whether you can extract work from it or not. So there is another problem here. It's called problem of battery. So what a battery does, a battery basically takes energy from a system. That's the charging cycle. Then it stores the energy. Then it releases the energy. Right? And you will say that battery is good if it charges fast, stores longer without decay, and then discharges also fast when you collect it. Right? So it turns out that you can make quantum mechanics gives you some advantage in that process. So these are called quantum battery problems. So you can think of a microscopic model of a battery. Again, you don't have to, of course, think in terms of whether you are going to actually make the battery. But if you can, that's of course better. But the idea is, can you use quantum mechanics to do this process where it's absorbed energy from a system and release the energy into the system, and how it holds the energy in the system can be tuned in an advantageous way. And if there is a bound on that, so it turns out there are bounds on this thing, which comes from uncertainty principle. So those are very interesting problems of this sudden approximation. Okay, you got an idea about the problems? What? Yes. No, then you will get, so yeah, so the point is, if you calculate the delta E with a critical point in between and calculate the delta E without any critical point, the main point is there is a significant difference between these two cases. There is a characteristic difference. And actually, I can tell you also this difference. If you calculate this delta E versus GC, you will see that it behaves like this. So if you calculate the derivative of del E del G, you will find this. So this helps you to calculate. If there is no phase transition, you will not see this characteristic difference in derivative. Okay. So this is a very new kind of problem which people are studying very recently. But this is a method to detect a phase transition, a quantum phase transition. Now, why it is a useful method? Because it's often not easy to do things with the ground state. So this problem actually involves all the excited states of the problem. So if you can find a method, so generally what do we say? Whether we want to know whether a phase transition happened or not. Now this picture is for ground state only. It may not be easy to actually probe the ground state. Right? It may not be easy to even probe a state. How do you image the state? That's a very difficult problem. People do that also. There is something called tomography. People can image a state, but it's generally very hard to do that. Okay? So then you want to do something else that tells you that phase transition happened or not without access to the states of the problem. So what do you look at? You look at the energy emitted or released, which is spectroscopy. So doing something to the spectroscopic level, you can detect a phase transition in the ground state. So these are the sort of advantages. These are the sort of things one has to think. So in principle, of course, you can calculate all those things, but how do you see that in an experiment? So you have to think in terms of easily accessible quantities. So energy difference is the most historically easily accessible quantity. That's the first thing people ever measured. That's why people discovered quantum mechanics. So now I have mapped this problem of a complicated quantum phase transition into a problem of spectroscopy. So that is the kind of advantages you have when you want to work with this. In this particular, this is just an example. There are many such examples. So there is this whole another problem is this. So if any of you, none of you actually attended this member effect talk, that's why I cannot tell you much about it. But the idea is if you suddenly cool something, the member effect idea is if you suddenly cool a hot object, it goes to its ordered state much faster if it is hotter to begin with, right? So it basically tells you if you put water in freeze, it will become ice, right? But it will become ice faster if the water is hot to begin with, which is counterintuitive. Now, generally it is said there is no explanation, people debate on it, but yeah, I think it's in terms of free energy one can think about this problem because it is not just the energy, but it's also the entropy. The entropy matters, right? So that is one way to think about it, but there are other complicated factors. So then if you try to think about the corresponding quantum problem, you will find many interesting issues. So for example, there is, when you take this system from here to here, right? Now if you quench it very quickly, you will find the system goes in a state like this. So this system is actually not this. It is a superposition of this and this, right? This is the ground state, superposition of this and this. So if you quench it, it will form these domain walls. It will form this domain wall. So each of these things is called domain wall. They are actually topological excitations. You can show that. Now, how many domain walls will be formed? That depends on how fast you are quenching it. Right? So there is a law called Kibble-Zurek law. And this law was originally discovered in the context of cosmology, actually, in certain problem of inflation and all. Okay? But then the people found this, and in basically in helium states, helium superfluid state and all that. So then people found the same law appears in many different kind of system, widely defined kind of system, and it's universal. So how many defects will appear? That is universal. Okay? That doesn't matter the details of the system. It just matters that you are going from one state to another, without a state to another, and how fast you are going. Okay? And eventually, if it turns out, if you make a sudden approximation, the number of domain wall will be infinite. Infinite means every other spins will be flipping. So there are very interesting problems. So these are called defect generations. There are a lot of interesting research going on in this defect generation in quantum phase transition, quenching across a quantum phase transition. So a lot of problems are there to study basically, but we don't get to do that in the course. I just gave you a glimpse of this idea and gave the simplest possible problems. Okay, then I will talk about the adiabatic approximation. So this is very interesting. Just think about this. So I started with a state like this, all the spin in x direction. Right? And then I suddenly quenched it to a Hamiltonian, whose ground state is this, the new Hamiltonian. So how it will evolve from here to here? So think about this. In terms of order disorder, one can think this, but if you have some other problem, if I quench means sudden approximation. Okay? How it will respond? So this is some HI, whose ground state is this. This is some HF, whose ground state is this. Of course, it doesn't mean that it will become its ground state. So this is a misconception many students have sometimes. That they say, if I change it, it will become ground state of this. It will not. Right? It will become it will be this state, then it will evolve in time to some state. So then the problem of how it evolves to some state and how much overlap it has with this actual ground state is a very interesting problem. So this is the problem I was trying to do in this helium atom. So what I said, my initial state is this hydrogen atom with two neutrons and one proton. I suddenly quench it to another helium atom, which has two proton and one neutron. Right. So how much overlap I have between these two wave functions? That was the problem we just. So they are prototype problems, but they are very different and very interesting in many different contexts. Okay, so now I'll do adiabatic approximation. Okay, I don't think I'll reach scattering today, but it's okay. Okay, the next thing I'll do is little non-trivial. Non-trivial, although you might intuitively think it is easy idea, but in showing it is a little bit of work. So this is basically the adiabatic approximation. So the idea is following, that if you have some initial Hi that goes to Hf very slowly. Now again, what does it mean by slowly? Slowly means again that it is much slower than the h bar by delta. Right? So the time scale of this is much greater than h bar by delta. So then what happens? So then the idea is, it's a quasi-static process, which you must have learned in thermodynamics. That means at every instant of time, so here I started with, let's say, some eigenstate. So it will remain some it or some psi t, some eigenstate of ht at that instant. Okay. So this is what I expect, but it's not so obvious immediately, right? So that's why it requires some work. But this is the statement. So this statement is called adiabatic theorem. So it says that if you go slow enough from an Hi to Hf at every instant of time, and you start with some eigenstate of Hi, at every instant of time, the system will remain an eigenstate of the Hamiltonian at that instant time. Okay, so this is the theorem. So let's try to prove it. Let's try to see that why it is true. And so in order to do that, let me use a parameter, h lambda, and h lambda as eigenstate n lambda, which is n lambda, n lambda. And lambda is something that is changing with time. Okay? And lambda is some function of t. And adiabatic theorem tells you if lambda, let's say there are many lambdas, many parameters, changed slowly, system will cling to the n lambda. System will cling to the n lambda. Okay, so let's see that how it is true. So let's say I have the time dependent Schrodinger equation. And I write down an unsatz solution, and the unsatz solution is this. Okay. So this has two parts. One part is obvious. One part is, so zeta m. It is 1 by h bar, 0 to t, dt prime, dt prime. This is basically just coming from the time evolution, right? That will be always there. Now this part will determine whether this statement is true or not, right? So if there is another time dependence which is not a function of time evolution, and that has some non-trivial dependence, then this theorem is not true. Right? You understand the answer? Everybody? Yeah. So I write down a general form of solution for this. Okay. And I said that it will be always true that this psi t will be a function of some, because m lambda t is basically a complete set of states. Right. So it should be always true that psi t is a function of some expandable at some m lambda t. But what kind of time dependence the coefficients will have? There will be one time dependence which is coming because of e to the power minus iht, right? Which is obvious. But then there is another time dependence which could be there, if this thing is not an instantaneous eigenstate of this. Right? So this extra time dependence is what that we want to find out. Now what do we want to prove? We want to prove that this object will be an eigenstate of the ht at that time. Right? When that will be true? If this amt is nothing but a phase factor. Right? So then it is nothing but a phase factor times the usual time dependence times this. Then you can absorb this phase factor here and say, okay, the phase factor doesn't matter. Right? Sorry, say that again. Yes. 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 It has a non-trivial time dependence. Yeah. So I want to prove that this AMD is a pure phase factor. Right? If it is a pure factor, then psi t is basically e to the power I is IMT m lambda m let's say tilde. It is absorbed into that. Then that means it's an instantaneous eigenstate of that. That is what I'm trying to prove. That is my agenda. If I cannot prove that, then this is not true. So let's see how to prove that when it is true. We want to see when it is true. Okay. So when it is true, I will plug this into this equation. Everybody got the idea, right? What I am trying to do and what is it? Any general time dependence problem had these two parts, right? One part that is coming from this some kind of time dependence. So in perturbative problems, we divided into two parts. One is the zero part, another is the di part. But this is not a perturbative problem. Here I am just saying there is one part which is because of the total Hamiltonian or the instantaneous eigenvalue at that time. Another part which is something that tells you this is not a simple, this has a non-trivial time dependence. This coefficient has a non-trivial time dependence. Then it is no longer an instantaneous eigenstate of that Hamiltonian. Right? Because now if you try to do this psi t as h at that t, you will not get et because of that extra time dependence. Everybody got this point, right? Those who are avoiding eye contact. Are you also clear about this? Online audience? Why not?
Yes, sir.
Very simple for you. Okay, so I want to prove this. Is it true or not? So what is the form of this? Basically, I want to find what is the form of this without any previous assumption. So what do? I plug this into this and I get the following equation. Am dot e to the power I is Im m lambda plus am e to the power I Im del lambda I m lambda I dot. So I wrote with the lambda I, but I can get rid of the lambda I also, because I just meant to say there are many lambdas. But if I put the I, you can also put the I back and imply the Einstein convention. So Einstein convention is basically this, that if I have I, that means there is an invisible summation on the I. So I can say that there is an invisible summation on the I if there are repeated index. But if you are not comfortable with it, just say del lambda, one parameter, not I parameters. So if I take a derivative, this is what you will get. Okay. Why do you get that? Because you will now have a notice that this lambda is a function of t. So because of chain rule, you have to do this del del lambda. Okay. Okay. So now I take a inner product of this with n lambda. I take a inner product, and when I do that, I separate the this term because I do n lambda here. N lambda are the instantaneous eigenkets at that lambda, right? So they are orthonormal. So that means this term will drop out, and you will be left with a n lambda sum of m a m e to the power I zeta m minus zeta n n lambda del del lambda I. Did you get an idea that how this second term came, or you are completely clueless? If I plug in this into this, what will we get? If I tap to take a derivative of this, where are the time dependence? There are three places, right? One is here, another place is here, another place is here. Right? Now, how will this time dependence show up? You can break it using a del del lambda del t, right? That term is trivial because that will just give you the et. Yeah, that term is here, right? Yeah, so am dot. Yeah, you can take this whole, so this whole quantity, no, it is not dependent on time. It is, well, it is dependent like this with the explicit t factor. So you take the derivative that tells you this is constant within this time interval. So you will only get a et, right? You will only get a e to the power xi m. Okay, so show this. I think this will become 0, this second term. So d dt of e to the power I GMT. This term, right? So I think this will become 0. Just show this. How do you show this? What? It will be? So what do you get here? You will get the IEM first comes down, right? So you will get e to the power I GMT d GMT, right? So this quantity will give you, yeah, there will be an I. There is another I in front of what? No, this I is here. This, you are talking about this. No, it is getting cancelled on its own. Yeah, okay. Yeah. Yes. Yeah. There are. Yeah. The point is, see. Yeah. Of course, you can take this kind of derivatives. Like. My point is. Yeah. E of t prime is constant for that time interval. Yeah. So that's why this becomes 0. Yeah. That is the point. So Et prime is a constant function in this time interval. What is RHS? What am I taking to 0? I didn't. No, what is your point? I didn't get it. Yes. Yeah, this term. You're talking about this term, right? This term. Yes, here. Okay. Yes. Oh, okay. I see. I see. Yeah, yeah. So this no, this will not vanish. Okay. So what will happen is this. So this HT at psi t is basically ET at psi t. Right? So this you have to use. Okay, get the details. I mean, this term will vanish, basically. Okay, so what do you get is this, n dot is this. So now there is another term, I missed that. No, there is no other term. So this is basically this and lambda I dot. Okay, so n dot is basically this, and I can now write, I can separate these two terms, which is n equal to m and n equal to m. So I get n dot equal to I a n in ai lambda I dot and minus m not equal to n. I'm just separating n and m equal to n and m not equal to n. Getting okay. So here ai lambda is basically ai lambda is just shorthand of this quantity minus I n lambda I. Okay. Everybody got this time? It is just expanding this thing into the term where m is equal to n and the term where m is not equal to n. Okay. So then I have one more quantity to evolve. That is this term. This term is a little weird. So let's evolve that. So take the time derivative of this equation. So take the time derivative of this equation, and you get lambda derivative del lambda I h m plus h del lambda I h. Okay. I am taking a del lambda derivative in this side. I'll first take a derivative of h and leave the m, and then take the h and do the derivative on m, right? And the left side is del em del lambda I m plus em del lambda I. So then I multiply with n on this side, and I get n.
Sir,
Yes.
sir, students have come for next class.
Yeah, yeah. You can leave that room. I'll just finish these two lines.
Okay, sir.
Yeah. Lambda I dot. Okay. I'll get em minus en. So let me just skip one step. I'll get em minus en, because in this case the h will directly act on this n m. So this term will come because of this, that left hand side. This right hand side will come because I act n on this, so it will give me en with a del lambda I. This term is also coming because of the same reason, and you will be only left with this. But this is a this is just a scalar, so mn orthogonality will give you 0, right? So you are left with this, and so that tells me I can now calculate this quantity in. So because using this inequality, I can calculate del lambda I n lambda I dot is basically n del h del lambda m lambda I dot em minus en. What did I do? I just left this and took this in denominator and multiplied both sides by lambda I dot, right? So now what does that mean? So now this term is basically equivalent to this quantity. Okay? So now I have a very simple argument. What I'm saying, that if lambda I dot is much smaller than em minus en, then I can throw away this whole term, right? What does that mean? That means rate of change of lambda is much smaller than the energy gap between the two levels, right? Then I can get rid of this term. So now it's a trivial problem, because now what I have to solve, see, the proof is quite non-trivial, although the statement is very simple. The statement is it's an instantaneous eigen. So then I'm left with this. Then I have to solve only this equation. Okay, and this solution is nothing but an. This is a constant times n, so it is Cn e exponential okay. So that means I just got the result that psi t is Cm e to the power I gamma mt e to the power I zeta mt times m lambda t. So this term was coming because of the zeta. This term came because of this, all this solution, that is this dependence. So this zeta is nothing but 1 by h bar em t prime dt prime. This gamma is basically okay. Notice that this is actually an integral over lambda, d lambda, right? So I converted this into an integral over time by taking this di dt, d lambda dt. Okay. So now this is a pure phase factor. Because of this form of the solution, this is a pure phase factor, right? So what did I conclude after all this algebra? I conclude that I started with, if my solution of this problem is still an eigenket of that instant of that h lambda, but with an additional phase factor, which is dependent on how you arrived at that lambda, right? So that, first of all, that proves the adiabatic theorem. but it has a non-trivial consequence. It has this additional phase factor, right? So this additional phase factor that must have some consequence. So we will come to that. But did you understand up to this much? Okay. So I will continue. I'll finish this discussion today. But of course, you can imagine I'm not going to ask a question asking you to derive it. So if you only care about the exam, you can leave. Otherwise, just listen that there are very interesting consequences of this. But did you get the point? What did I say so far? Okay. So now something very interesting will happen. There will be no questions for this in the exam, just so that I make it clear before you complain that classes are extending. Okay, so notice that what happened. So we just proved that at every time, so I go from hi to hf, at every instant of time, ht, the system, if I start with some eigenstate n, the system will be nt, okay, will be at nt, but with the additional phase factor, I gamma n nt. Okay. And there is of course another factor which is already inside this, which is this zeta, which is because of the normal time evolution. Okay. Now this factor is very strange because this factor tells you dt prime a lambda t lambda dot. Right? This is the factor. This is the extra factor. Okay. Now, what does it mean? So where did it come from? Okay. So let's see that. So what is this A? First of all, this is another point to remember. So A is basically minus so I del lambda I. So actually I should not use the I here and there. So let me use N and P. So it is a matrix of this derivative. It's a matrix element of this derivative operator, which is basically the rate of change of lambda. Okay. So it tells you that how are you changing it, what kind of trajectory it is following in this lambda space. Okay. So this term is called Berry phase. Actually, nowadays it is called Berry Pancharatnam phase. So Pancharatnam was a physicist at RRI. He discovered a similar effect in optics before Berry, but it was not very. It was not that much. It didn't get that much attention until Berry rediscovered it in context of quantum mechanics. So we should actually honor the person who actually did this first. Very Pancharatnam phase. And this has a very interesting consequence. So this is an observable object. So I will not go too much further. So let me just give you one quick example. So let's say I have some manifold, a manifold of parameters lambda, some high dimension, because lambda is a high dimensional object. So if I have a Hamiltonian with many parameters lambda, right, and they are changing with time. So that means the Hamiltonian, the system is traveling in this high dimensional manifold. Okay. So now if I do a problem where I go from some time initially, I go take a round and come back to the same parameters wherever I started. Right? So then this integral will become this. It will be a round integral on that. But that means the system will hold the memory of where it traveled, the traveling path, right? So this calculation suggests that, right? So the final state of the wave function will have the memory of its past history. Okay. So this is a detectable object. So this thing is called, and the Arnav-Bohm phase you learned earlier is basically this object. Okay, you can connect this with that. And there are interesting topological consequences with this, and this is actually also leads to some kind of a gauge theory, which I will not talk about right now. The kind of gauge theory that you have learned earlier. So again, remember where the gauge theory come from. Gauge theory means you do some changes in your fields and potential that doesn't change the measurables, right? So this is that basically, it's a phase factor. Right? So yeah, this is basically the Berry phase is the topological Berry phase. This thing turns out to have something. So if you're, yeah, so let me make this point. So let's say if this is a manifold with some pinch point. So if you take a handkerchief and pinch one point, right? So this is called the pinch point. Or you can think of something else also. So let's say it's a this manifold has a hole. It's a torus, or it's a like jalebi, right, with many holes, right? So then it's a like topologically very non-trivial. So then if this doesn't have any hole, you can shrink this path to 0, right? But if it has a hole and you make a path like this, then you cannot shrink this path, right? So then these two objects are topologically different class of objects, right? There is no continuous deformation that allows you to go from one to another, right? Now what is more interesting, that is where physics and especially condensed matter physics is very cool. This thing can be connected to a transport experiment, a linear response experiment. So you can show that this fact that this can be shrink to 0 and this cannot be shrink to 0, they will give two different response in the current conductivity of these two systems. So if you calculate the current operator, so you know how to calculate current, right? If I give you grad J plus del rho del T is the continuity equation. So you can, rho is your charge density wave function, psi dagger psi. That is, its derivative is this. So J is psi grad psi. So this is basically imaginary part by some h bar factor and all, right? So if you calculate the current in this object, and you can do a linear response theory, calculate the conductivity and everything, you can show that they have characteristic differences into them. Okay, so if it means that if you put a current in this object by some inject a current by some battery or something, right, they will show you a response which is signature, which will carry that signature, whether it's built on a manifold that has a hole or not. Right? So this is actually was observed in this quantum Hall effect. So if you calculate the Rxy by B, so this is a 2D plane put on a magnetic field, you will see that. So this kind of step-like structure in the resistivity, and the steps will tell you what is the topological number of that system. Okay? So this is where it is actually manifested. It is not just some abstract parametric space and all that. It has a real world consequence. Okay. So there are very interesting extended problems which are not very well understood. For example, how do you formulate a heat transport? This is a very interesting problem, because if you think of a disturbance in this electrical transport, it will be in the Hamiltonian, right? It's basically an electric field or magnetic field that is that will feature in the Hamiltonian. Right? If it is a magnetic field, you will change the P to P minus E square, right? If it is electric field, there will be some rho E type coupling. But this is even a classical problem, that temperature doesn't show up in Hamiltonian, right? So how do you deal with temperature? If you want to do a heat transport, you have done this experiment like Joule effect, Seebeck effect, right? Where you take a rod, one part in ice, another part is lamp, so heat is transporting in that, right? And there are thermoelectric response and all that. So there are very interesting questions there, that how does this topological effect show up in those problems, and how do you formulate that, because it doesn't feature in the Hamiltonian. Right? So there are ways to handle that. People use a fictitious potential and try to fix that problem. But that's a separate discussion. But within this discussion, I'm just giving you an initiation of this idea, that how these Berry phases are so important, that they can carry topological signature, and also if they can carry a signature effect in the phase, which you can detect by some interference experiment, which is this Arnaud-Bohm interference experiment is one example of that class. Okay. And they are purely, these phases are purely topological, purely quantum mechanical phenomena. There is no classical analog to that. So you can also show that. So if you do that for certain systems, this term will tell you all about its unique quantum mechanical features. Okay, so there is just one more point which I will not do, just mention that these things you can formulate it just like electrodynamic gauge theory, because these end of the day it's a gauge term, and there are things called Berry curvature. So these things are expressive. You can write down, for example, in electrodynamics, you have a F term, right, which is del lambda. Uh, what is the X term? F look like? Can you remind me? It is del lambda a nu, right? And sorry, and del nu a lambda, right? This is your F nu. This is your F term. You learned that unit so much strange. You have not learned electrodynamics, huh? The F field formulation of electromagnetism in terms of these tensor fields. Are you sure you didn't learn? It's there in Griffiths. Okay. You started, it was done, or you didn't study because it was not in exam or something? Okay, okay. So then let's not discuss this. But you can formulate the electrodynamics in terms of this F field. Then instead of this 4 or 5 Maxwell equation, you'll have just one Maxwell equation. So you can write it as some. Okay, I wrote down that equation somewhere here. So look it up. It's very simple. It's reformulation of electrodynamics. There is nothing new. I think you can write it as some del F equal to 0, some form like that. Okay? And you can actually write a differential geometry form. Then it becomes d star F equal to 0. So more and more sophisticated, the whole Maxwell equation becomes this one equation. Okay. So it's just compressed way of writing everything. Okay. So then it is actually the advantage of doing it is that it's unification. All of sophisticated theory is basically for unification. Now you don't need an electric field and magnetic field. You just have one 4-vector field which is A, and it's this thing is called some tensor curvature, and you just have that, and that will define the whole electrodynamics. And that is possible because these fields are basically, they are not two separate entities, they are like similar entities. So now you can formulate a F for this A also. Okay, you can formulate this problem also in that language. So I'll not, okay, they're good that I didn't go into all that. Okay, so this is just the idea. So read up this covariant formulation of electrodynamics. You have learned the relativistic electrodynamics, right? Then it will be a big problem in QFT course. So I think I have to design my syllabus with, this is a problem almost every year, but this year it is my problem. Other years it was someone else's problem. Okay, that's the main difference. So I have to. Like in quantum mechanics also that is happening. But I told that explicitly many times that relativistic quantum mechanics should not be a part of quantum 2. It should not be by any means, because it's impossible to do justice. And because of that, I am shortening discussion at many places such that I can touch that, which is not a good thing, because this discussion should be done in great detail. Anyways, that's all for today. And there are very interesting things in both these points.